In part 2, we will get some more details about this Reynolds average Navier-Stokes equations and Reynolds test terms. We will also get to explain about the closure problem. In the second part, we will explain why the problem of closure still remains. So, if I write the equation and bring it to the other side, the new term, if I bring the new term from left hand side to the right hand side, the same average Navier-Stokes equation can be rewritten in this form. The left hand side does not have that new term, that is brought from there to the right hand side. The left hand side remains the same as the original Navier-Stokes equation, except that we use average quantity. Right hand side first term pressure gradient term, the viscous diffusion term is also there, but we have that additional term written and included in the derivative term. Now, these equations are specially called Reynolds averaged Navier-Stokes equation, in short form RANS. Now, this additional term rho ui prime uj prime, if you substitute units, so rho is a density and u is a velocity, if you substitute unit and check, it will have the same unit as mu into dou u by dou xj. Mu into dou u by dou xj is actually a stress. So, this quantity new term rho ui prime uj prime also represent stress, and that is why we brought these two terms together and grouped them, and the derivative is taken separately outside. Now, in expanded form, that is by substituting value for I and j following that index notation guideline. For example, ui prime and uj prime, we substitute I going from 1 to 3 and j going from 1 to 3, we get u prime squared, u prime v prime and u prime w prime, and the derivative denominator we have xj, xj, xj and xj index is repeating, and for every value of j you get one term, but then they are added, and that is why you get here summation term. Next value of I, again j, we get another term, for next value of I and j we get another term. These terms are additional terms appearing in the Navier-Stokes equation because of the procedure that we have followed, decomposition of the variable, following tensor algebra, performing averaging, it will result in additional term called Reynolds test term. R I j is a symbol used, equal to minus rho ui prime uj prime. In terms of matrix, and I can write all these additional terms in form of matrix as shown here, rho u prime squared bar rho u prime v prime bar rho u prime w prime bar and other quantities. Now, if you look at each term little more detail, along the diagonal as I am showing here, you have u prime squared bar, v prime squared bar and w squared bar, and these are all what is known as a normal stress. So, along the diagonal element we get normal stress. Off diagonal elements, for example, u prime v prime bar, u prime w prime bar, v prime w prime bar, these are three off diagonal elements on one side. Similarly, we have three off diagonal elements on the other side, and these 3 plus 3 6 off diagonal elements are called shear stress. So, following the convention sigma for normal stress and tau for shear stress, we write in the form of a symbol for the stress on the right hand side corresponding left hand side. Minus sign is retained and rho is retained. Let us put that equation again, but in slightly different form. We know from one of the beginning lecture that left hand side there are two terms, one is for time derivative, other one is for convection term. The time derivative term represent local acceleration, convection term convection acceleration, and if you put them together that will give total acceleration, and that is what is shown here with a capital D symbol. So, rho into d by dt of u I bar. So, this represents total acceleration written with average quantity. On the right side you have a pressure gradient term, then there are two terms. We know already this mu is a viscosity, and mu into dou I by dou xj we give you the stress, and it is contribution from laminar part. So, we write tau ij with a subscript laminar dou by dou xj, and the second part we use again the same letter symbol tau for stress, but it is for turbulent flow. So, we have dou by dou xj of tau ij with a subscript turbulent. So, what it means is the equation looks similar if you put laminar stress part and turbulent stress part together, there is only addition of turbulent stress part. And task of turbulence modeling is to model these additional stress term, that is rho u I prime u j prime bar. Now, let us look at little more detail. We already mentioned turbulent flow exhibits fluctuations both in time as well as in space, and it is quite random. That means, it is difficult to predict what the fluctuation will be either at the next instant of time or at the next spatial location, but what is possible is a statistical way of dealing with those variations. Now, if you look at this term, it is u I prime and u j prime. U I prime is fluctuation of one variable and u j prime is a fluctuation of another variable. We do not know the u I prime itself, then it becomes much more difficult the product of two variations. Hence, we have to model somehow and replace the governing equations accordingly, and that process, that stage, that procedure is called turbulence modeling. I am showing here the same equation in a much detailed form without using index notation. The first set we have Navier-Stokes equation, this is otherwise Reynolds average Navier-Stokes equation, and you have bottom continuity equation. All these terms are already explained. Now, you can definitely appreciate using of index notation to write terms and finally equation. So, we have 3 terms for convection, 3 terms for stress, and we have 3 equations, all are compressed in one simple expression when you use index notation. And these stresses, additional stresses are known as Reynolds stress. They are also written in matrix form, and we already mentioned elements along the diagonal, that is u prime squared bar, v prime squared bar, w prime squared bar, they are all normal stress, and off diagonal elements are shear stress. And we write again that equation. Now, you appreciate difference between writing the index notation and in expanded form of writing equation. So, we write here again the Navier-Stokes equation obtained for turbulent flows as shown here. We will try to get some more explanation. We rewrite this equation in the form as shown here, minus 1 upon rho dou by dou x j p bar delta I j, this is a Kronecker delta, plus mu into dou u I bar by dou x j plus dou u j bar by dou x I minus rho u I prime u j prime bar. We identify the terms as 1, 2, 3 inside the bracket. Let us get explanation of those 3 terms. the first term represent mean pressure stress. The second term is because of the laminar viscosity, that is a dynamic viscosity mu. So, it is called mean viscous stress tensor. It is mean because we are using ui bar and uj bar. The third term is actually Reynolds stress tensor, and this is coming extra term because of the averaging procedure applied on the convection term. If the modulus of the Reynolds stress term, that is ui prime uj prime bar modulus rho, is much greater than the laminar stress part, then that actually is the region of turbulent flow. In other words, in fully developed turbulence at large RE, the role of viscous stress is negligible when compared to the role played by Reynolds stress. Let us try to understand what is the meaning of closure problem. So, in the original setup, we have continuity equation 1 equation and Navier-Stokes equation 3 equations, and there are 4 variables, that is u, v, w, each velocity component, and pressure is additional term. So, there are 4 variables and we have 4 equations. Number of equations equal to number of variables is satisfied. In equation for turbulent flow, we just now learned you have still 4 basic variables, that is 3 mean velocity and mean pressure. In addition, you have 6 Reynolds stress term, but number of equation remains as 4 still. Hence, condition that number of variables equal to number of equation is not satisfied, and this results in well known problem called closure problem. That is, we have more variables. In turbulent flow, you have 10 variables, that is 4 primary variables, mean velocity 3, pressure 1 and 6 additional stresses. So, we have 10 variables, whereas number of equations available are only 4, that is 3 momentum equation and 1 continuity equation. Hence, we have more variables than number of equations available, and this is what is known as a closure problem. There is a way to solve this closure problem. Either you can get additional equations for each of those stresses, or suitably replace the unknown variables in terms of known variable, hence number of unknown variables gets reduced. In turbulent flow, it is possible to derive additional equations for fluctuating quantities and then find out also the equation for Reynolds stresses. But every time you write additional equation, it will only end up in more unknowns. Hence, the closure problem remains. The alternative way is to suitably replace unknown variables, that is the stress ui prime uj prime bar in terms of known variable. This process, that is replacing unknown variable by a known variable, is what is called turbulence modeling. So, in today's class we have learned in detail about equations, continuity equation, momentum equation, how to put them in index form, then how to apply decomposition principle for each variable and get continuity equation, momentum equation for turbulent flow. Momentum equation, when it is applied to turbulent flow after averaging is performed, is referred as Reynolds average Navier-Stokes equation. We learn while doing this process, it results in 6 additional unknown stress quantity, and they are to be replaced with the known quantity, and this procedure is called turbulence modeling procedure. In the next class, we are going to talk about different models available. Until then, have fun. Thank you.